Hi everyone, I'm excited to share with you today our most recent work using and modifying 3D chemistry climate models and exploring a range of habitable zone planets. Due to the time constraint, even though I do have two topics listed here, I'll be focusing on this latter one, namely the effects of stellar UV and X-ray radiation. I'd like to first acknowledge my co-authors, Allison, Hwchen, Eric, Adina, and my advisor, Dan. A few decades ago, these are the three known HZ planets. Over the past few years, since Kepler, we've been rapidly filling out the known population of HZ planets. Of particular interest are planets orbiting KM dwarfs, and thus we need to understand their habitability and their observational prospects in preparation for future missions. The host star environment can greatly affect the properties and atmospheres of the attendant planets. Importantly, most of the stars in the Milky Way are M dwarfs. Probably most of the stars in the universe are M dwarfs. Thus, understanding planets around M dwarfs is important. This also means that what is true for planets around M dwarfs should then, by extension, be true for most planets in the universe. Our previous work exploring inner edge habitable zone planets around a range of M dwarfs found that only planets around active M dwarfs in a UV can be pushed into the moist greenhouse regime as defined by the Casting 1988 paper. Even in cases in which the stratospheric water vapor mixing ratio goes beyond or enters the Casting 98 classical moist greenhouse threshold, the thermospheric hydrogen is still low due to a range of reasons. Most importantly, if the activity of the M dwarf is low. In that case, photodissociation will be very inefficient, which would lead to the resultant low thermospheric hydrogen mixing ratio and low escape rate. Thus, the UV context, in particular the constraint of the UV emission of M dwarfs, are critical in assessing whether the planet is truly in a moist greenhouse water loss regime. That work explored climates using steady state spectra. In our most recent work, we've leveraged time-dependent flares from a range of surveys in order to assess and simulate their effects in a 3D chemistry climate model. Importantly, M dwarfs are expected to exhibit frequent and high magnitude flares similar to the Great AD Leo flare observed by Hawley and Peterson in 1991. M dwarfs are expected to emit frequent high energy flares that dwarfs even the largest solar flare, which is 10 to the 21 ergs. Previous 1D work found that while a single large flare does not substantially perturb a planet's ozone layer, recurring flares could quickly destroy the entirety of a planet's ozone layer, given an initially Earth-like atmospheric composition. 3 dimensions are the natural next step. This is because an important regulator in how flares can affect planets is the magnetic field. In this case, showing in this cartoon, a magnetized planet can redirect and deflect charged particles, incident charged particles to the poles. On the other hand, if the planet is unmagnetized, the majority of the charged particles and all of the UV radiation interacts or gets deposited in the dayside hemisphere. In our study, to explore the magnetized planets around sun-like stars versus unmagnetized planets around low-mass stars, we leverage test data as well as MUSCLES data and use them as inputs to our 3D chemistry climate model. We then take these simulated results and input them into our radiative transfer atmospheric spectroscopy code developed by the Seeger group to assess the effects of flares on the transmission spectrum of various types of planets. To get the proton flux, we cannot rely on direct observations of distant stars because the measurement of ionized particles released from stars is currently not possible, but we use an observed relationship between solar X-ray intensity and proton flux to calculate the proton fluence in each flaring event. And here's our result. We find that flares drive substantial perturbation in the atmospheric chemistry, especially nitrogen oxide, hydrogen oxide, and ozone. And these 3 gases are particularly important because they affect the chemical abundance of a range of other gases. So these are the first 3, especially NO and OH. These 3 gases, or these 2 gases, are the most directly or initially affected species by the incident protons. And by the way, showing here is a scenario for a magnetized planet. And we can see that the spatial distribution does confirm that it is magnetized, given that most of the effects occur in the poles during the flare peak. So this is a mixing global distribution of the mixing ratios of NO. We can see that the incident cell protons are redirected to the poles, and during which protons associate N, oxygen, N2 and O2, which then produces NO. You can see there's a small effect on ozone during strong flaring, and this small destruction seems to persist due to repeated flaring. So 30% isn't that large, but that's for a magnetized planet around a sun-like star. For an unmagnetized planet or unmagnetized planets around the K and M dwarfs, the scenario is different. Due to the stronger flaring scenario stronger magnitude flare and more frequent flare that I alluded to earlier, the dayside also directly interact with the incident UV irradiation and incident protons. And this creates a much more different scenario in which during repeated flaring can drive significant deviation of the chemical compounds from its initial state. Comparing to in the G-dwarf planet scenario, in which the chemical abundances, specifically the NO and OH abundances, quickly returns or tries to return to its baseline during or after a large flare. On the other hand, we could go back to the K-dwarf case, most of the chemical abundances, as more importantly for habitability, the ozone abundance, quickly deviates or gets destroyed from its initially abundant state. I should note that both of these scenarios use the exact same proton frequency, incident proton frequency. Thus far, we've discussed modern O2-rich conditions. What about the flare effects for O2 poor and more highly irradiated moist greenhouse atmospheres? Well, interestingly, as shown here in panel B, that the flare peak NO production for both the O2 rich and the O2 poor atmospheric compositions are comparable, despite them having very different O2 concentration and NO concentration during the initial baseline pre-flare state. Another interesting result is that flares can drive temperate surfaces into moist greenhouse upper atmospheres during the flare peak. And this feature is persistent in terms of its large water vapor inventory with repeated flaring. So this means that moist flares can drive temperate atmospheres into moist greenhouse states, which can allow the subsequent dissociation of water vapor and allowing the hydrogen to escape via diffusion. And finally, I'd like to leave you with my takeaway message slide, and thank you all for your attention.